So the work at Imperial College is rather complementary to the physiome work. But there are many aspects, in particular an aspect that I'll talk about today, which is complementarity, makes a direct connection. So there are various people at the Institute for Mathematical Sciences, in aero, in computing, in math, and also in medicine, who are working in this program. And the idea of the program is to be driven by clinical hypotheses and clinical procedures and clinical applications. And sort of the flow is from the clinic into mathematical modeling, data acquisition, data analysis, and we talked about, we heard about analyzing some of these complicated signals earlier, and also close connection with imaging, as well as the simulation. And so we're hoping that we can make a sequence of these networks work to start with a hypothesis and check these hypotheses. The program only began in January, and we have a few postdocs and a few graduate students. So the main message today is that although the wave motion of electrical activity potential and the change of shape that it induces are quite physically different problems, the dynamics share the same mathematical principle, which is this principle of optimal paths, which is the subject today. The geometrical compatibility of these two problems invites a coordinated approach, and this is the approach we're trying to take through to combine the various types of data, but also using this concept of motion along optimal paths. So one common basis of the two types of problems, the wave propagation and along with the change of shape, is that this is what Sasha already talked about, how the conductance metric allows itself to be incorporated into the shape metric. I think you'll see, I can point to it in the equations in a second. And so the compatibility of the two approaches provides a platform for data fusion of shape and wave configurations. So here's a typical data fusion problem from MRI and CT fused together in a clinical setting with the catheter, because you see in the clinic you can't see much about the heart, but if you can fuse this, if you are able to fuse the data from the MRI and change the shape of it, right, as it's moving, then the person in the clinic knows where he is in the heart with the catheter, and the anatomy of the heart varies is very patient specific. I took a course in cardiac anatomy, and I held a lot of hearts in my hands. They're amazingly different from person to person. Okay, so the other aspect for today is in the heart we have these isochrones, right? These are the level sets of the phase of the wave at a given time, right? So this is the early arrival set, this is the late arrival set, isochrones. Then when you see this picture, you know you're looking at a wave. You can think immediately of Huygens wavelets. If you're looking at a wave front at a given time, it's precisely when the signal arrives, and one of these lines, of course, is an isochrone. It means that the wave is along this contour at that time. Okay, so there typically is three types of propagation models. The full-scale biophysical models, which seem to be a lot of the emphasis today. The phenomenological models with reaction diffusion equations. The iconal models, which are these optimal propagation models, basically the Huygens principle models. Okay, so an example for the monodomain model is a reaction diffusion partial differential equation. It's familiar to most of us, but I want to point to this particular aspect of the tensor conductance, which is the source of this anisotropy, and there can also be inhomogeneity in that tensor. And it fits directly into the model that Sasha showed, where if you let S of x be the arrival time for the reaction diffusion wave at a given location x, the minimum, the critical principle for this this form of the arrival time, which is just the length, the time it takes to get there using this inverse of the conduction tensor as a metric, gives an equation which is called the iconal equation, and the time-dependent version of that equation is the Hamilton-Jacobi equation. There's been a lot of work in this area, a lot of really interesting work that points to this geometrical approach. So the solutions show the spread of the isochrones, and they don't spread as circles in a plane if you have an anisotropy. Instead, they have this other aspect to the iconal equation. Okay, so these isochrones are the geodesics, or least time paths, of the for the spread of the EAP through the heart. Now, we know that the wave that comes first is the only one that matters in the spread of EAP, because that's the wave that depolarizes. And the wave that comes, any kind of signal that comes second has nothing to do, right? So this is the principle for Huygens wavelets in this case. The wave that gets there first does the excitation. Okay, so the first punchline is that optimal paths apply to cardiac isochrones, and these are basically geodesics of least time in Fermat's principle. So we might call this cardioptics, right? It ignores the wave profile and it just describes the wave front, propagation of the wave front. So in finite dimensions, these optimal paths satisfy ordinary differential equations, and this is their typical form. It's the form that people either love or hate, right, when they see this tensor here with this the Christoffel symbols in it. But if we were going to now try to make the isochrones coordinate with the change of the shape of the heart as it beats, then we would need to have an analogous equation to this one, which is on the space of shapes. Shapes, well, what is shape? Right? You can think of a shape, right? The sphere. And if you choose whichever shape you'd like to look at as your reference shape, and that's the point. You could just look at it forever if there wasn't another shape to compare it with. So we want to find the paths that take you from one shape to another, as when the heart contracts. And these paths are in an infinite dimensional space of smooth invertible maps. So we think of shape as the action of a smooth invertible map on some reference shape. This is very close to what you do in fluid dynamics. You think of a reference configuration of the fluid, and then you move it forward by a smooth invertible map, which is the flow of the fluid. Okay, so for us in images, there are two features. There's the shapes and the picture. Now, in image processing, there are two main processes: registration and segmentation. Now, and it turns out that the space of invertible maps, of the diffeomorphisms, divides globally into two components. One component is the space of shapes, okay, which is, we think of it as oriented vertically over a point here, which is in the space of densities. And if we have a picture, we can change the shape of the picture by deforming the space, leaving, say it's, if it's a three-dimensional picture, leaving the volume invariant. And then we can, if we wish, also think of a change of the picture as it changes volume, say, from one point to a point along the flow here. So a usual change moving from one shape to another will be some curve in the combined space, and it consists of a vertical part, the change of shape, and a horizontal part, which is the change of the picture. The vertical part corresponds to registration, and the horizontal part corresponds to segmentation. And so this is mathematics. This is decomposition of the process of imaging in an infinite dimensional space into a vertical and a horizontal part. Okay, here's an example. This goes back to Darcy Thompson, who compared species of fish by looking at the shapes. Well, that's what they did back then. They looked at the shapes to see something about families of evolution. How did I lose this? I don't know what happened, but I'm glad it's back. Okay, so this fish and this one each have names. Darcy Thompson knows their names. Is if you draw the picture on this grid and then expand the grid, right? It takes you from one fish to another. But this is exactly what we're thinking about for these images. We're thinking about changing the space on which the image is drawn as along a path. Okay, so what we want to do is apply this to geodesics taking us from one shape to another in the heart. I'm not going to be able to tell you much more, but I will show you the equation that allows you to make these comparisons and to define a path length for shape. It's my favorite equation. It's called EP_diff. And let me show you what it does. See, it'll take a vertical line into like blowing a bubble. It allows shapes to bend and turn. This is just the evolution of this equation. This is the equation which is the optimal flow from one image to another one. And this is in 2 dimensions, and here it is in 3 dimensions. And the point is that this equation, EP_diff, allows large deformations, and it comes from the same source. It comes from the source of optimal paths in this other space, the space of shapes, as opposed to optimal paths on the substrate of the heart, which is what the isochrones are from. Oh, thank you.
Okay, thank you very much.
Questions?
No, questions?
I just want to raise a technical point. Beautiful map for following the wave front,
Yes.
but a
I
lot
know
of
your
it
question.
has to do with the wave tail. So you
Right.
said it's the first wave that activates. It's the first wave
Yeah.
that activates first. It's the
Yes.
second wave that can kill you.
Absolutely. I agree with you, Al. And there are people in the audience, Olivier and Sasha and Hans Dirks. If you take a look at Hans Dirks' poster, you can see the recent steps in that direction. Obviously, you want to control the front and the back front. Okay? Any other questions? Yes.
There are great presentations. One question I have, and that's a question also to people like Sasha and others. This scaling, to me, doesn't seem to be quite the same thing as occurs, say, if you have additional tissue. So if you expand an excitable medium is one thing. If you add additional excitable media, you
Yes.
may have completely different behavior. Or am I completely wrong?
You're absolutely right.
Okay.
Is there's change of shape and there's growth. Okay, and I didn't talk about growth here, but one of the reasons for splitting the space into this vertical and horizontal is that growth is on the horizontal, right? And so the number of white pixels increases. Yeah. Yes.
You showed this picture with
the anisotropy, and it was one direction of anisotropy with a different velocity. Is it possible to include local anisotropy, different orientations?
Yes.
So in the symmetric-
In the monodomain model that I showed, the tensor conductance depended on where you were, so it could be changing in space, and it doesn't have to have just one direction. It
and
has
also for this chair.
three eigenvectors. Yeah, okay, sorry.
Okay, thank you very